Everyone, good morning. I assume people can hear me. First of all, thanks to the organizers of Microservices Day for having me here. My name is Diptanu, and I work in the cloud platform engineering group at Netflix. I work on large-scale distributed systems, things like data center operating systems, Mesos, Linux containers, distributed persistence, IPC, and things like that. Anything that relates to scale and public cloud and things like that. Um, so in this talk, I'm going to be mainly talking about web operations today. This topic is very dear to my heart. So when Fred suggested that I speak about it, I was like super happy. Sean did a good job about talking about why they do microservices, what are the advantages of doing microservices, so I won't go into that. And if you are convinced that you should be doing microservices, so I'm going to be talking about the consequences of doing microservices and what happens when you do microservices at scale, and what happens if you do microservices at scale and on public cloud. Traditionally, taming things in production environment meant controlling like how things flow, controlling how soon software goes into production, and being very strict about change controls, right? Speed of innovation and turnaround time is very key at Netflix. We design things so that we can move fast, and when we move fast, things break. And we have learned over time how to embrace failures, and in this talk, I'm going to be talking about how we keep things sane while moving very fast and moving things into production several times a day, several hundred times, deploying software several hundred times in a week. So Netflix is a large-scale TV and movie streaming company. We have awesome originals. Recommend watching Marco Polo, like that's my favorite. And we are currently over 50 plus countries and at 62 million users, 62 million and more users. We run a very tight ship to make sure all our services are highly available. We do currently like over 2 billion API requests, and we have over 500 microservices which power the Netflix service. Each microservice is operated by the engineers who write them. So people like me who write those services are on pager duty. Everybody in the company is on pager duty. So that means we don't have any separate dev and ops team to manage services and separate teams who write services. So we are responsible for the uptime of the services. So what it means is that for us, it's crucial that we write services in a manner that we know how they can fail, and so that like we can sleep through the night. So literally, whenever we design a new system, we are talking about what is going to happen when it breaks at night. Like, how are we going to get through the traffic of Christmas evening, for example? And how is the system going to be breaking on Christmas evening? Or what happens when you come home and you are watching TV? What do we do to make sure that the Netflix experience doesn't degenerate? So when I say that Netflix is powered by 500 odd microservices, I literally mean it. This is the graph of one of our mid-tier services. It's fanning out to like hundreds of microservices and data tier services. And each of these services are usually managed and run and designed by a team of 6 to 7 engineers, or in some cases, like it's even less. And in some cases, it might be more, but the more would be probably lesser than, like maybe like 3-4 engineers writing and managing each of these services. Netflix is on the public cloud. We are on AWS. We operate all our services in an active manner and across multiple geographies. At any given time, we can handle disruptions to any AWS regions where we operate. Few years back, if you remember, I think it was year 2011 or something, on Christmas Eve, most of the major popular websites on the internet were down, including Netflix and others who operate on AWS, because there was an ELB outage. So things like that doesn't hamper our service anymore. Like, we can move traffic from one AWS region to another. Not only that, like if our services degrade, because of a thundering heart problem in one of our services, we can move from one region to another. So for the rest of the presentation, I'm going to spend a lot of time about talking about failures. And failures are a key aspect to any distributed systems and to microservices. And I want to impress upon you that when we are talking about microservices, we are talking about giant distributed systems. And no discussion about distributed systems is going to be complete without talking about failures. So what the canonical explanation of failure means lack of success. So we are going to be talking about what we do at Netflix when things fail and when one or more services fail. So failures can be correlated directly with the speed of change and the scale, right? So if you're a telco where you are moving things slowly, like you are deploying internet routers which don't change on a daily basis, or if you're NASA who have deployed software on New Horizon, which is being running for the last 30 years, chances are that the software is not going to break, but the hardware might fail, right? And if you are a small shop where you are not deploying fast and also the scale is small, chances are that everything is going to be working because things don't change so much, and over the time things become stable and services work fine. And if you're a startup where you are innovating rapidly, innovating every hour, changing directions every few days, but the scale is small, chances are that software will break but not hardware. Because the scale is going to be small. But at internet scale, at web scale, when the speed of change is really high and also the scale is really high, everything breaks. And at Netflix, we are at the top right corner because we are deploying so many times in a day and so many times in a week because of the change in the business needs and change in how our traffic is scaling up and down. So we see things breaking at hardware, we see failures at network, we see our software failing. So the key thing is to remember that everything is going to fail all the time. And in a microservices architecture, the most unfriendly operation is the operation which takes over the network. The network has to be treated as unreliable. And what is hard about predicting network failures is that the failure can happen at the network layer, or it can happen because there is a busy neighbor problem if you're on the public cloud. You might be running with some other customer of your cloud vendor, like who are probably saturating the network substrate. And even though you are not doing so many gigabits or megabits of network traffic, you might still see like failures because the network links can be saturated. And failures can be at the other side of the connection. The host to which you are making a network call might fail. So predicting where failures are happening on the network is like really hard. So most of the challenges that people solve on distributed systems and on microservices architecture is like, how do we deal with network failures, right? Hardware failures happen too, like you might see that the underlying file system is failing, or if you're using something like ZFS or copy on write file systems, you might see that the more you write or read into the file system, the performance of the file system is itself degenerating, and at some time of the day when the graph goes up and up, you'll see the software is going to be breaking unpredictably. And of course, there are bottlenecks in software design, which often comes from undesirable spike in traffic, like traffic during Super Bowl or traffic during, for us, like traffic during Super Bowl dips, but during the intermission, we see lots of people coming back to Netflix and watching stuff. So Super Bowl is still a problem. And then Christmas Eve as well. And then there are problems of widespread failures, right? So in distributed systems and in microservices, what happens is when something fails, we see like cascading failures all over the stack, right? And there can be failures in the data center itself, like the control plane of your cloud provider might not be working for some time. What it means is that you can't scale up. So what do you do at night? What do you do when people are watching TV? Do you shut down your service? No. So what happens is that as developers, we have to embrace those kind of failures and think about how do we mitigate those. And for the rest of the talk, I'm going to be talking about how we solve each of these problems. The first key thing to my mind that comes when I write a service at Netflix is that I know that this system that I'm writing is going to be failing, and everybody knows that. Murphy's Law, everything is breaking all the time. So the first key thing is to make sure that when things are failing, things degenerate gracefully. What it means is that if you're watching Netflix, if our API is down, if our Lolomo service or the service which tells you what movies you might like, it doesn't mean that we give you like a blank TV screen. We should still show you like some content which may be less relevant to you, but still like you don't get like an empty screen where you don't watch anything. So the first key thing is making sure that things degrade in a graceful manner, and when things fail or when things degrade, like as engineers, we should be able to detect those failures really quickly and fix those problems really quickly. And the key is that, and we often joke about it, is that we should not fail for the same reason. So it's okay to fail, but it's not okay to fail for the same reason, maybe twice or thrice, or maybe when traffic increases 10 times more. So how do we tame all the complexity? At scale, we can't treat the cloud as a co-located collection of servers. At Netflix, a unit of deployment is a cluster of thousands of compute nodes in an ASG. So we use ASG or auto-scaling groups on Amazon and treat it as a unit of deployment, right? So we don't deploy like one single server, or we don't see the performance characteristics of a server. We see the performance characteristics of a cluster, and then we debug things at a cluster level. We monitor things at a cluster level. We do failovers at a cluster level. So that makes that, even though like we run so many services and so many servers, that makes it more manageable now, because we are not talking about 60,000 servers or 80,000 servers in one Amazon region. We are talking maybe about 500 clusters or 600 clusters. So that lowers down the complexity. And then we do immutable images. What it means is that in a cluster, we can be rest assured that everything, all the software that we deploy are same. We don't run Puppet or Chef during the time when we deploy our software. And when we deploy our software, we know that the software is already there in the server, so there is no invariance in what bits are actually getting deployed. That helps tremendously. And then we measure everything that we can measure. The biggest expense of our cloud infrastructure is actually our monitoring system. I think we are spending 40% to 30% of our expense in the monitoring system that we run. While we monitor everything, it's key to monitor like some key metrics so that like at a glance, like you can say that this is how our service is performing. And if those key metrics dip, then we boil down to the finer grain details. And then one of the things that I think is really key to running things at scale is backward incompatibility of API. So what it means is that at night when I wake up, when my service doesn't work, I can easily go back to my old version of the service. Now I can go back to the old version of my service only when I have maintained backward compatibility. So it's very easy to break compatibility with the API as developers, but to run things in production, to run things at scale, like making sure APIs and data models are always backward compatible is very essential. And then we have a good continuous delivery pipeline story. We can move things from test to production in a matter of like 15 minutes. I'm going to not go through the details of our continuous delivery stuff and how we test things in production, because I think the speaker next to me is going to cover those in details. But that's like a really important thing that you need to have when running things at scale. Have the ability to move things from test to production really quickly and test things whether things are working. So I was talking about the network being unreliable. So we try to have a good story around IPC. IPC stands for inter-process communication. Traditionally, people have been talking about IPC in the context of operating systems where two processes are co-located. In our situation, we are talking about IPC across the boundaries of two different servers. What it means is that this mechanism, the IPC mechanism, has to be designed for sustaining failures. The IPC mechanism has to be glued with the service discovery, right? So service discovery is like a phone book or like a registry of all the services that are running over the network. So it's very key that the IPC mechanism or the REST client or the remote procedure client that you have is like very tight and close to the service discovery. And our IPC mechanism at Netflix like reacts to network latencies. So what it means is that in a cluster, if there are 5 bad servers because of Java doing garbage collection for a few seconds, or like the file system getting corrupted, or like the data, there is like a request getting blocked. What it means is that our IPC library handles those latencies and balances load on the servers which are healthy. What is interesting here is that we do client-side load balancing. We don't have like software load balancers or hardware load balancers between 2 servers. So what it means is that our clients, the IPC client, is itself doing load balancing. So we also skip like 1 extra hop in the network. And I think it's really cool. It works really well. The other thing is when you have a dependency of a user request on hundreds of microservices, so if you have like a front-end service which is running Tomcat or Jetty or something like that, and if you have a request coming through and you have 4 different dependencies which are microservices, what would happen is there might be one dependency which might be like getting really bad. By dependency here, think of a dependency as a microservice. So what it would mean that the user request, even though the other dependencies are really working well, the user request is going to be taking as much time as the bad dependency is taking. So if dependency A resolves in 10 seconds, not 10 seconds, 10 seconds is really high, but say like 100 milliseconds, but dependency I is returning in like 3 seconds, the user request is not going to be completed for the next 3 seconds. So what it means is that there will be now cascading failures. So at some stage, you will see that Tomcat or Jetty having lots of threads which are blocked because of dependency I, and so the whole cluster of the front-end service is going to go bad, and the user experience is thus going to degenerate. So what we do is that we have something called Hystrix, and it's open source. We make sure that there are fallbacks for every dependency. So if there is a dependency which has gone bad, we don't even make calls to that dependency or that service. Now the top level service will know how to serve fallbacks, and fallbacks are first class when we design any service. We don't treat any service that we depend on as reliable. Every service is allowed to break, every service is allowed to go down, but the service overall, which is user-facing, has to keep running. That's pretty much like the goal. And going back to Hystrix, Hystrix is basically like a library which encompasses all these patterns. So if you use Hystrix, then you are basically going to be minting your application with those patterns from the very get-go. We do reactive scaling. Since we are on public cloud, we don't always scale up to like 80,000 or 90,000 servers. Like we scale down whenever we don't have enough traffic, and whenever we have more traffic, we scale up. But the interesting thing is that when we have failures, when we have network outages or any service outages, we scale down. So when there is an outage, the key is to not scale up, because when you scale up, it means that you are probably giving more pressure to the services which are bad, and those services are even going to go worse. One thing that I have learned while doing operations at scale is that the lesser traffic you have when things are bad, the more faster things recover, and the faster things recover, you can eventually scale up. We have a service called Scryer, which basically understands how a service has been scaling based on historical data or on the last 10-15 minutes, and based on that, Scryer does predictive autoscaling. So what it means is that we don't have to rely on the floodgates to open and then scale up. We scale up before the floodgates open. So we do linear regression models, and based on those linear regression models, like we predict what number of servers we should be running with. And lastly, I love this paper on designing and deploying internet scale services by James Hamilton from Lisa07. He says that failure recovery should be a simple path, and it should be tested, and we take that very seriously. We have our simian army suit of monkeys. We have like I don't know, like a dozen monkeys running in Netflix on the Netflix cloud, making sure that we are inflicting pain on ourselves. The first monkey that we run on a daily basis, on an hourly basis, is Chaos Monkey. It kills nodes in a cluster. So if you are running things like Zookeeper or your databases, Chaos Monkey is not going to tell you that it's killing servers. It's going to kill servers, and it's going to test whether your service is still up. In AWS, we are evenly spread across multiple availability zones. What we do is that we kill one zone or more than one zone by Chaos Gorilla. And when Chaos Gorilla attacks, like we see 2/3 of our servers disappearing all of a sudden. And we see like what happens when 2/3 of our servers disappear. And the next is my personal favorite, Chaos Kong. What Chaos Kong does is Chaos Kong takes down a whole data center. And in the context of Netflix, a data center is pretty much like an Amazon region. So what happens when we take down a region is that we flip our DNSs to make sure that user traffic is routed to the healthy data centers, and we scale up our data centers. And since we use linear regression models by Scryer, what happens is when traffic is gradually moving, like we are exponentially increasing the number of servers that we have in the healthy region, and hence we are able to serve like the whole country or the whole continent of Americas and now Europe as well from one data center or one Amazon region. So the key takeaway of my talk would be to design to embrace failures and not treat dev and ops as two different aspects. Treat web operations as something which is first class. Treat web operations and operations of running services at scale while you are writing the services. Every line of code that you write, I would say that treat that every line of code to be unreliable. Every network call that you are making, treat that network call to be unreliable. People complain when they see a lot of error handling and exception handling on languages like Go. But I think like exception handling and error handling at the site where you're making a network call or a call onto the file system is the right thing to do. Whenever there is a dependency, any software that you are not writing should be treated as unreliable. Any software that anyone tells you to interact with should be unreliable. The operating system should be unreliable. Everything is unreliable and everything is going to break. That's the message. And we write on our tech blog very frequently about how we write systems, about historics, about reactive scaling, and what we do to run services on AWS. Visit them, and if you're around, I would love to chat with you about how we do things. So that's pretty much it.